Hello, data science students. I hope you're all staying happy, healthy, and safe. So last time we left off talking about the concepts of what logistic regression is and how we can use it to model state changes. And we also talked about how this is used a lot in psychology and perception research, and sometimes referred to as the psychometric function. So I actually have an example of this being used in the wild. So this is real, actual data from a study that one of my grad students, Jonathan Hopper, if you're out there watching, hey! This study actually ultimately led to a large part of his master's thesis, which he's going to be defending in a couple weeks. Good luck, dude! Anyway, so this was a function this was a study designed to model the function of how people detect whether or not their speed while moving through a virtual world has changed, whether or not it was going faster or slower than they were going originally. And what we find is this beautiful, beautiful logistic curve. And turns out in VR, people were misperceiving their speed. So they tended to think they were going slower than they actually were, which meant they had to have a higher speed change in order for them to detect themselves as going this, or in order for them to feel as though they were going the same speed as they actually were. It's just really, really cool data. I really love this study. But this is just an example of how you might actually use this for real, actual data analysis. So moving right along, what does a logistic function look like? Well, the logistic equation looks like this right here. It's actually very simple, very straightforward. 1 over 1 plus e to the negative x. The only variable in this whole thing is this x. So, which looks a lot better for us than, say, our linear regression model did. Our linear regression model, we had to figure out slopes and intercepts, which, that's kind of crazy. 2 whole variables. This is just 1, so it's got to be easier, right? Well, maybe, maybe not. Let's think back about our linear regression model again. So this is what our linear regression looks like, our linear model, our slope-intercept linear model specifically. So we have our intercept plus our slope times x. And again, we had to figure out a couple things. We had to know our x value already, which if we're plugging that in, we do, but we had to figure out our slope and our intercept. Let's play a hypothetical for a second. Let's say, hypothetically, we had a slope of 1 and an intercept of 0. What would that line look like? It would look like this. It would just a diagonal line going through our origin. And if we work this out, what would that equation look like? Well, it looks really simple. Y equal x. Now, I'm playing a little bit of mathematical trickery with you here to make a cognitive leap to something else. But this looks fairly familiar, right? Y equal x. Y equal x. Where have we seen just a lone x already? Why, my goodness, we've seen it in the denominator of our logistic equation. Well, here's the thing. Even though we can't model state changes using a linear model, turns out the only variable that's in our logistic equation typically changes linearly. Which means if we can actually figure out a set of x values from our data, we can do a linear regression of that, and then use that linear regression of these exponents in the denominator to perform our more complicated and cool state change model using logistic regression. Now that's really, really neat. That's pretty robust. So we actually end up taking this and changing it into something that looks like this, where instead of having x, a single variable, we actually have a function, a linear function. And so as long as we can figure out the linear model for these exponents in the denominator, we can figure out what the logistic equation looks like, or what that logistic function looks like, and do a logistic model. Now, this is something that we've learned to predict already. We've learned how to do that, but in order to do this, we have to know some examples, some training data, so to speak, for what that equation should be. So now we've got to figure out the values to perform this linear regression on. And so that's a little bit frustrating because, well, now it seems that Dr. Jones has given you something to do that you don't really know much about. But don't fear. If we look at the y-axis of our plot from before, what's this weird little word here? Ah, we've got probability. That's interesting. Well, turns out you can actually do the same model as a probability ratio or an odds ratio. And I think that's what my next slide is. Yes, probability. So we can represent the same function as the probability of an event occurring divided by 1 minus that probability. And turns out what we can do, we can get the exponent that's going to be in the denominator by taking the natural log of this equation. Come on, I'm talking ahead of my slides. There we go. Now this is great. This is good. It gives us something to figure out. But darn it, Dr. Jones, you keep giving us stuff that we don't know. We have to find this new thing. We got to figure out what the probability at an x value is. Well, maybe we do, maybe we don't. So if we actually look at the plot, like I pointed out earlier, our y-axis is the probability. So if you average together the yes and no responses, or your state 1 and state 2 responses for each of the age groups you're looking at, you suddenly get an average probability within that age group. And this is something that we can now use to figure out the pattern within our exponents. Now, one of the issues is, in order for this technique to work, you're going to have a fairly large set of data, and our couple hundred sample sets isn't going to work very well for us. And so let's pretend that we went out and collected much more data. Specifically, we collected about 1,800 samples, and we've associated our blue points with no and our orange points with yes on our plot. Now this is a lot of data, and if we scatter it out, you can see how numerous the values are. But since they're all sort of compacted into 1 and 0, yes and no responses, they all just kind of blur together along each of those directions. Now what we can do is we can bin this data, and so by binning the data by year, so we end up having each of these little columns of data being 1 year of age, we can get the average yes or no response, so the average probability of a yes response for each of those age groups. And this lets us calculate a probability for each of these years. And by using our equation from before, getting the natural log of our probability ratio at each of those years, what we end up getting is the exponent that's going to be in our denominator. Now this looks like a linear set of data, and that's because it is. Now we have something that we know how to work with already. By using our linear regression technique, we can actually model the change in the exponents in the denominator of our equation. And this gives us a model that we can have a slope and intercept with. And then, using this, we can plug that into the logistic equation. And so taking that, and we can now generate, come on, change slides, there we go. We can now generate a logistic state change model using a more simplistic linear regression model. So fundamentally, logistic regression models state changes, and the exponents in that function typically vary linearly. So by using our linear regression technique, we can essentially do this more complicated modeling technique of the logistic equation. So again, this is something I mentioned before. Keep in mind that this modeling technique describes probabilities within a population and doesn't describe probability for an individual. So it's a method used to determine the likelihood within a certain segment of a population for a state change to have occurred. Okay, so we're going to wrap up our presentation there. And if you guys have any questions, please feel free to send me an email or come to my office hours. Again, if you want to come to my office hours, here every weekday from 4 to 5. I encourage you to come and chat, ask any questions that you may need. And you can get to my office hours either from my Ole Miss webpage or my personal webpage. There's a big blue button on the front page. Click it and enter your official University of Mississippi email address. Okay, so wrapping it up there. If you guys have any questions, please let me know. Otherwise, I will see you in cyberspace.